Find the characteristics value and the characteristics functions of the Sturm's Liouville problem d over dx into x dy upon dx plus lambda x into y equals to 0, where y dash 1 equals to 0 and y dash e raised to power 2 pi equals to 0, where we assume that the parameter lambda is non-negative. Solution: the given Sturm Liouville's problem is d over dx into x into dy upon dx plus lambda upon x into y equals to 0, y dash 1 equals to 0 and y dash e raised to power 2 pi equals to 0. This is equation 1 and this is equation 2. Now differential equation 1 can be written as x d square y upon dx square plus dy upon dx plus lambda upon x into y equals to 0, or x square into d square y upon dx square plus x into dy upon dx plus lambda into y equals to 0. Equation 3, substituting x equals to e raised to power t in 3, we get dy upon dx equals to dy over dt into dt over dx equals to 1 upon x equals to dy over dt, or x into dy over dt equals to dy over dt equals to d over d into y, where d equals to d over dt and x square into d square y upon dx square equals to d square y over dt square minus dy over dt equals to d into d minus 1 into y. Then from 3 we get d into d minus 1 into y plus dy plus lambda y equals to 0, or d square into y minus d into y plus dy plus lambda y equals to 0, or d square plus lambda into y equals to 0, or d square y over dt square plus lambda y equals to 0. In this problem we have, this is equation 4, in this problem we have lambda is a non-negative, so we consider these separately. The case lambda equals to 0 and lambda is greater than 0. The case 1, lambda equals to 0. The differential equation 4 reduces to d square y over dt square equals to 0. The general solution of this differential equation is y equals to c0 t plus c, or y equals to c0 log x plus c. In this general solution of 1 we have, this is equation 5, in the general solution of 1 where lambda equals to 0, now we apply the condition to the solution of 5. The condition to applying for this equation, so condition y dash 1 equals to 0 implies 0 equals to c0 upon 1, or c0 equals to 0 because y dash x equals to c0 upon x. Condition y dash e raised to power 2 pi equals to 0 implies 0 equals to c0 upon e raised to power 2 pi, or c0 equals to 0. Both these conditions does not impose any restriction upon c. Thus for lambda equals to 0, we obtain the solution of y equals to c, where c is an arbitrary constant. Now these are non-trivial solutions for all the c not equals to 0. Thus lambda equals to 0 is a characteristics value, and the corresponding characteristics functions are given by y equals to c, where c is an arbitrary non-zero constant. Case 2, lambda is greater than 0. Now equation 4 reduces to d square plus lambda equals to 0, where d equals to d over dt, which employs d equals to plus minus square root of minus lambda. These roots are conjugate complex numbers since lambda is greater than 0. So the roots can be written as plus minus square root lambda into iota. Thus the general solution of 4 may be written as lambda equals to c1 into sine square root lambda t plus c2 cos square root lambda t. Thus the general solution of 1 may be written as y equals to c1 into sine square root lambda log of x plus c2 cos square root lambda log of x, because x equals to e raised to power t, which implies t equals to log of x. This is equation 6. We now apply the boundary conditions of 2 to the solution of 6. From the 6 we get dy over dx equals to y dash x equals to c1 square root lambda upon x cos square root lambda log of x minus c2 square root lambda upon x sine square root lambda log of x. Equation 7. The conditions y dash 1 equals to 0 for 2 to 7 gives c1 square root lambda cos square root lambda log of 1 minus c2 square root lambda sine square root lambda log of 1 equals to 0, because log of 1 is 0. So c1 square root lambda is 0. So thus we must have c1 is 0. Equation 8. Now condition y dash e raised to power 2 pi equals to 0 of 2 to 7 gives c1 square root lambda e raised to power minus 2 pi cos square root lambda log of e raised to power 2 pi minus 2 square root lambda e raised to power minus 2 pi sine square root lambda log e raised to power 2 pi equals to 0. Since c1 is 0 and log of e raised to power 2 pi equals to 2 pi, this reduces to c2 square root lambda e raised to power minus 2 pi sine into sine 2 pi square root lambda equals to 0. Either c2 equals to 0 or sine 2 pi square root lambda equals to 0. Since c1 is 0, the choice of c2 and would gives us the trivial solution. So we must have sine 2 pi square root lambda equals to 0, and hence 2 pi square root lambda equals to n pi, where n equals to 1, 2 and so on. Thus for the non-trivial solution we must have lambda equals to n squared upon 4, n equals to 1, 2 and so on. This is equation 9, because 2 pi equals to square root lambda equals to n pi, which implies 2 into square root lambda equals to n, or which implies 4 lambda equals to n square, which implies lambda equals to n square upon 4. Corresponding to these values of lambda, we must obtain the non-trivial solutions. Y equals to cn cos n log of x upon 2, n equals to 1, 2 and so on. Equation 10, here the cn equals to n equals to 1, 2 and so on are the arbitrary non-zero constants. Thus in this problem the values of n, lambda equals to 0, 1 upon 4, 1 and n upon 4, 4 and so on, n square upon 4 and so on. For n is greater than equal to 0 are the characteristics value of the functions. Y equals to c0 and c1 cos log of x upon 2 and c2 cos log of x and c3 cos log of 3, c3 is cos 3 log of x upon 2 and so on for n is greater than equals to 0, where c0, c1 and so on are arbitrary non-zero. The constants and are the corresponding characteristics functions.